All right. So again, when you have your spheres on the corners, and there are 8 corners on a cube, so when your atoms, which are spheres, are on the corners, 1/8 of that sphere is inside of your cube. When you have a face, 6 faces on a dice is a cube. All right, so when you're on the face, 1/2 of your atom is inside of the cube. So over here, we're looking at a cube, and the cube that we're looking at is this one. All right, so this is the cube that we are looking at. All right. All right, so when we come over here, this line right here is this one right here. All right, so when you have this, you're going to see that you have all of the green, which is the chloride ion. So all of the green ions are on the corners, and they are also on the faces. And so we have the CLs. So the Cl minus, that is the green, bigger green sphere. All right, so we have the 8 corners. And so 1/8 of that is inside of the cube. So on the corners, we have 1 ion in the cube. We have our 6 faces. 1/2 of that chloride ion is inside of the cube. And so that is 3. So we have a total of 4 Cl minuses inside of this cube. All right, so now the smaller purple ball here is the sodium cation. All right, and so we have them on the edge. We haven't really talked about edges, but when we are on an edge, 1/4 of your atom, or ion in this case, is in the cube. So when you're on your edge, all right, so we see that we have 4 of them here, and we have 4 of them here. And if you can't see those 4, it's this one, this one, this one, and this one. And then you have 4 in the back. So you have 4 here in the back. 1, 2, and 3, and 4. So you have your 4 in the back. All right. So there's 12 total edges on a cube. And so you have your 12 times your 1/4. That is 3 of your Na plus ions inside of the cube. All right, and then you have this one right here, which is in the middle of this cube. All right, so in the middle, you can't see inside of this middle. All of the ions are covering up the middle, but there's one in the middle. And so you have a total then of 4 Na pluses and 4 Cl minuses, because we know the formula of sodium chloride is NaCl. So you have to have an equal amount of sodium cations, and you have to have then that has to equal the amount of chloride anions. And so it could have been 1 to 1, it could have been 2 to 2, it could have been 3 to 3, 4 to 4. Well, it was 4 to 4 in this case. We know the ratio had to be a 1 to 1 ratio inside of that repeating cube. All right, so you need to know that if it is on a corner, 1/8 of it is inside the cube. If it is on the face, 1/2 of it. On the edge, 1/4 of it. In the middle, the whole thing is in there. All right, so if we look at this structure, all right, so you have the zinc plus 2, that's the dark spheres. All right, and so this is your zinc plus 2, this is your zinc plus 2, this is your zinc plus 2, and this is your zinc plus 2. All right, and so all of your zincs are inside of the cube. So this is 4 zincs in the cube. All right, and so your S minus 2s, those are all the light gray. All right, so all of these So note your S minus 2s. You have these 4 on the corners, and then you have these 4 on the corners. So you have 8 corners that have the S minus 2. All right, so you have 8 corners. Remember, a corner is 1/8 of the atom inside the cube. So that's 1 of your Sn minus 2 ion in the cube. Then your S minus 2s are also on each face. So S minus 2 is on all 6 faces. And so you have 6 faces. And again, 1/2 of that ion is in the cube. And so again, we have a 4-to-4 ratio. And it is 4 of the Zn plus 2s and the 4 of the S minus 2. Again, zinc sulfide is ZnS. So we knew it had to be a 1-to-1 ratio of the zinc cations with the sulfide anions. All right, and in this case, it is a 4-to-4. All right, so on the test, it's not going to be given to you as a zinc sulfide or a sodium chloride or a cesium chloride or anything that you could predict that it's 1-to-1. You're going to be given a structure like this, where the orange are going to be called atom A and the gray is going to be called atom B. All right, but it's the same exact thing. So the orange one, so the A, the orange, you've got your 8 corners, 1/8, and then you got your 6 faces at 1/2, and so you got your total of 4 A atoms inside of the cube. And then the B, again, that is already, all of this is inside, all of that's inside, all of that's inside, all of that is inside. It's not on a face, it's not on an edge, it's not on a corner. It is inside of the cube. And so you have 4 atoms of B as well. And so you have then AB is the simplest formula for that compound. All right, so we could say how many atoms of A are in the compound, or ions of A, and how many orange balls are in the cube. Okay, so there are 4 orange balls in the cube. How many gray balls are in the cube? There are 4 gray balls in the cube. All right, and so what is the simplest formula? Well, that is simply AB. All right, so now we're going to use the greatest equation in all of Gen Chem because I came up with it. That's why it's the greatest formula in all of Gen Chem. All right, so you'll never see this equation anywhere because I made it up. All right, so the volume of your cube is equal to length times width times height. That is your value of A. And that is mammal DNA, MM. Molar mass, L. That is not something you will ever see anywhere. It's my last name, Lou Waiters. That's why I made it an L. I had to pick a letter, and L is what I picked. All right, remember that is 1, 2, or 4, whether it is a simple body or face-centered cubic lattice. All right, DNA. D is your density, and A is Avogadro's number. All right, and so when you're given this question, these questions are very difficult, but if you use this equation, they are not near as difficult as long as you have the right units. All right, so we have silver crystallizes in a face-centered cubic lattice. So the face center has corners and it has faces. So all 8 corners and all 6 faces. 8 times 1/8 plus 6 times 1/2. All right, and so you have to know that a face-centered cubic has 4 atoms in the cube. All right, you will actually see 14 of them. 8 on the corner, 6 on the faces. That's 14 of your silver atoms, but we don't care how many silver atoms we want to know how many are in the cube. And only 1/8 if it's on the corner is in the cube, and 1/2 if it's on the face is in the cube. And so the L value here, L is always going to be either 1, 2, or 4. Simple body phase. So if it tells you it's simple, it's 1. Body is 2. Phase is 4. If it asks, is it simple, body, or phase, that means you are solving for L. And if you calculate it to be 1, it's a simple. If you calculated L to be 2, it's body. If you calculate L to be 4, then it is a face-centered cubic. But here they give us that. They tell us it is a face-centered. And so we know our L value is 4. All right, the length of an edge. All right, so that's A. A is length times width times height. And since it is a cube, they are all the same. All right, so it doesn't tell you if it's the length, the width, or the height because that is all the same distance. All right, and that is 408.6 picometers. Pico is 10 to the minus 12 meters. So if we want to get rid of the pico, it's 10 to the minus 12. It's also 4.086 angstroms. And remember, an angstrom here, angstrom is times 10 to the minus 10 meters, except we want the units for A to be in centimeters. And so it is a 4.086 times 10 to the minus 8 centimeters. And for all of these questions, your centimeters are going to be times 10 to the minus 8. All right, because it's always going to be in terms of angstroms. All right, so when you're doing your lengths, they are going to be in angstroms. Every time it's going to be some number and then a decimal point, and that's going to be in angstroms. And that is always 10 to the minus 8 centimeters. The reason why that has to be in centimeters, and we're going to have centimeters times centimeters times centimeters and get centimeters cubed, is because of the density. The density has to be in grams per centimeter cubed. And remember, if it's given to you in grams per milliliter, that is the same thing. All right, so a milliliter and a centimeter cubed is exactly the same. So if they give the density in grams per milliliter, just change that to centimeters cubed because a milliliter is the same as a centimeter cubed. All right, and so we're not going to calculate that part. We are going to use the atomic mass of silver from the periodic table, 107.87 grams per mole off of the periodic table for the molar mass, the atomic mass of silver. And we're going to solve for Avogadro's number. So we have to solve for Na, that is your Avogadro's number. All right. All right, so we have our volume of the cube is equal to A to the third, which is mammal DNA. All right, so we need to solve for Avogadro's number. So multiply both sides by Avogadro's number, and then divide both sides by A to the third. So multiply by Avogadro's number, divide by A to the third. Multiply by Avogadro's number, divide by A to the third. And so you have molar mass times L divided by D, and then your A is cubed. And then you just plug in your numbers. 107.86 grams per mole. It was a face-centered cubic with 4 atoms in the cube. Density was 10.50 grams per centimeter cubed. And A was 4.086 times 10 to the minus 8 centimeters, and that has to be cubed. All right, and so you're going to have centimeters times centimeters times centimeters when you cube that. And so the centimeters cubed will cancel the centimeters cubed. The grams and the grams per mole will cancel the grams in the density. All right, and so your units you're left with are atoms per mole, which are the units for Avogadro's number. And so when you push the buttons on your calculator, you get 6.023 times 10 to the 23rd atoms per mole. All right, and so the actual value is 6.022. So again, it is only different in the number that has some uncertainty. The last significant figure. All right, and so again, it could be solved for molar mass, it could be solved for L, it could be solved for density, it could be solved for A. You're going to have to solve for one of those, or solve for the volume of the cube. All right, so again, here is another one that's going to have a different unknown. But again, it's face-centered. As soon as you see face-centered, L is 4 atoms in the cube. All right, density, correct units. Great, atomic mass, AMU. Now, I never use AMU. Grams per mole for your atomic mass. All right, and now it says calculate the length of a unit cell edge. So now we are calculating A. Now we're looking for A. All right, and so we have the volume of the cube. That's equal to A, and that is mammal DNA. And then we just plug in our numbers. Molar mass, 195.08 grams per mole. L, 4 atoms. Density, 21.45 grams per centimeter cubed. And then Avogadro's number, which will be given on the test, 6.022 times 10 to the 23rd atoms per mole. And so the atoms will cancel the atoms, the moles will cancel the moles, the grams will cancel the grams, and you're going to end up with no units on top in the denominator, 1 over centimeters cubed, so you invert and multiply, and so you have centimeters cubed. All right, and so you're going to have your volume of the cube is length times width times height, a to the third. All right, and so when we get this answer, we will have to take the third root of this answer in order to get A. So you have to know how to use your cubed root on your calculator. And so then you will have your A value. When you push the buttons. What I do know is you better get times 10 to the minus 8 centimeters. If you're not getting times 10 to the minus 8 centimeters, you have the wrong answer. All right, and in this case, it is a 3.924 times 10 to the minus 8 centimeters when you push the buttons on your calculator. And it says, how does that compare with 392.4 picometers? Well, this is 392.4 picometers. All right, so that is the exact answer that we should have gotten, which is given right here. All right. So again, this equation is one that you should memorize. It's easy to memorize. Volume of the cube is length times width times height is equal to mammal DNA. Molar mass, L, the L is 1, 2, or 4. Density, Avogadro's number. They will do it a different way. If you like that way, great, do it that way. But that is a much more difficult way to do it, but doesn't matter. You get the exact same answer. All right, so chapter 12 is about solutions. All right, so when you make a solution, you're going to need a solute and a solvent. So we've already done this. All right, so you have your beaker and you've got your solute. And then you got another beaker and you have your solvent. All right, so universal solvent would be water. And then you mix them together and you have your solution. All right, so you need to know what a solute is, a solvent is, and a solution is. They are all different. All right, now your solute could be a liquid. We could have two liquids here. All right, if you have two liquids or if you have two solids, all right, your solute is going to be the one in smaller amount. And the solvent is going to be in larger amount. All right, and when you have a solvent, there is only one solvent. For your solute, you can have more than one solute. All right, so the one that has the largest amount, that is going to be your solvent. All the other things are going to be your solutes. All right. When you have two liquids, in this example, it's acetone and water, and they completely mix together, and it looks like one single solution. It is one single solution. All right, and when they mix together, when two liquids mix together, that is called miscible. They mix together. All right, if you put water with methylene chloride, or if you put water with gasoline, those things would be immiscible. They do not mix, and you will see a separation between the two liquids. All right, and so the liquid on bottom is going to have the higher density. Of course, the one on top is going to have the lower density. All right, so you need to know the terms miscible. That means they mix together. Immiscible means they do not mix together. All right, so if we are identifying our solute and our solvent, if we had 80 grams of chromium and we had 5 grams of molybdenum, all right, again, the larger amount is called the solvent. The smaller amount is called the solute. All right, if we have 5 grams dissolved in 1,000 grams of water, water is the universal solvent. And your magnesium chloride is the solute. That is a classic solution to be made. All right, so this one is the one I was talking about before. We have 39% nitrogen, 41% argon. The rest is oxygen, which makes it 20% is oxygen gas. So this has 3 things, not 2 things. All right, so again, your solvent can only be 1, and it is the one in the highest percent. And so argon here is the solvent. Always one solvent. All of the rest of those things are going to be solutes. So 39% nitrogen, that's a solute. The 20% oxygen, that is a solute. All right, so make sure you can identify your solute and your solvents in order to make solutions. All right, so when you mix your solute with your solvent, you're going to have 2 choices. You're either going to have a saturated solution, which means you added way too much solid and it will not all dissolve and you got solid on the bottom of your beaker. Or you will have an unsaturated solution, which means it all dissolved. And so you have a unsaturated solution. It could, if it's colorless, it will look just the same as water. All right, so it is completely dissolved in your solvent. All right, and that will depend on the solubility. So when we take sodium chloride, the solubility of sodium chloride is 36 grams per 100 grams of water. All right, so we can dissolve 36 grams of sodium chloride in 100 grams of water. All right, so we can make a saturated and an unsaturated solution. So if we're putting in 30 grams of sodium chloride into 100 mils of water, the density of water is 1, so that's also 100 grams of water. All right, so it will all dissolve. 36 grams would dissolve, so of course 30 grams will all dissolve, and you have an unsaturated solution. Now, if we tried to dissolve 40 grams of sodium chloride in 100 mils of water, well, 36 grams will dissolve, but 4 grams will not. So you're going to have solid at the bottom of your beaker. Anytime you have solid at the bottom of your beaker, you have a saturated solution. Not everything dissolved. All right, so if everything dissolves, you have an unsaturated solution. If you have solid at the bottom that will not dissolve, then you have a saturated solution. All right, and so since we were given the solubility of sodium chloride in water, we know that 36 of these grams will dissolve in the 100 mils of water, and 4 grams will not. So the 4 grams will be left at the bottom of your beaker. All right, so if you want to know if something is saturated or unsaturated, you just look for solids at the bottom. If you see solid at the bottom, you have a saturated solution. All right, but there is one other choice, and that is a super saturated solution. So in order to make a super saturated solution, you're going to add too much of your solute, and then you're going to heat it up to dissolve it. All right, and so you're going to take, whatever, the 40 grams of sodium chloride, and you're going to heat that up and keep stirring. And then you will get more of the sodium chloride to dissolve in the water. All right, so then you're going to cool it down to room temperature. All right, and you got to do that very slowly because your supersaturated solution is very unstable. All right, so if you shake it, move it in any way, it will quickly precipitate out. If it was the 40 grams of the sodium chloride, it'll precipitate out the 4 grams. For this example, they're using a lot more than 4 grams. All right, and so what they're doing here is this is a supersaturated solution. If you add a crystal, which is a disturbance, it will cause all the excess solute to precipitate out immediately. And so this just grows very fast and precipitates out all of your solid. All right, so a supersaturated solution is unsaturated. All right, but it is supersaturated. To tell the difference, if you had 2 of them and I said which one is saturated, which one's supersaturated, well, you just shake both of them, and the one that crashes out a bunch of solid, well, that was the supersaturated one. All right, so unsaturated, you can stir it, shake it, whatever. It's not going to do anything. A supersaturated solution, any disturbance is going to cause that to precipitate. But if you can't tell by just looking. You go shake them, then you're going to see this solid form, and you'll know that that one was the supersaturated solution. All right, so we said that you can have miscible where they mix, and you can have immiscible where they don't mix. To predict if it's going to be miscible or immiscible, we have to know what our solute and solvent are. And so we have the term here, like dissolves like. So if you have a polar molecule and you need to dissolve that, you need to use a polar solvent. All right? If you had a non-polar molecule, and you wanted to dissolve that, you would have to dissolve in a non-polar solvent. All right, and so like dissolves like. So the more like the 2 things are, the more that they will dissolve. All right, and so you want to pick a solvent that polarity matches the solute, and then you will know that it will mix. All right, so if you have 2 things that are different, they're going to be immiscible. So if you have things that are different and they are not alike, then you're going to have a polar and a non-polar, and you're going to have an immiscible solution. All right, so let's say we have 2 compounds. X, no dipole-dipole bonding. All right, so that means it is non-polar. All right, Y exhibits hydrogen bonding. All right, so that means that it's got all the forces. It's got the London, the dipole, and hydrogen bonding. All right, so now we can predict the solubilities, all right, of X and Y in water. So we know water is HOH. We know that that has hydrogen bonding. Again, like dissolves like. Y is going to dissolve in water. All right, X is not going to dissolve in water. X is nonpolar. Water is polar. All right, so you have your water molecule, it's bent, it is polar. Like dissolves like, and so Y has hydrogen bonding, water has hydrogen bonding, and so you will be able to dissolve Y in water. You will not be able to dissolve X in water because X is nonpolar. But if we used a nonpolar solvent, well, then we could dissolve the X which is nonpolar. We would not be able to dissolve Y because it is hydrogen bonding, polar. It's got, at London, it's got all three of the intermolecular forces. So in most cases, your solubility is going to increase with increasing temperature, but there are some compounds that will actually decrease when you heat up decrease the solubility when you heat it up. But most of your solids will be more soluble when you heat up your solvent. All right, so again, you got your hot pack, you got your cold pack, so you break the barrier, you're going to mix these things up. Usually it's something that dissolves in water and gets hot. This is something that dissolves in water and gets cold. Not necessarily in water. Sometimes it's just something that reacts with air. They'll break something to let air in and it gets hot. But you have an exothermic process and that gets hot. You got an endothermic process and that gets cold. All right, so now we're going to look at solubility of gas in a liquid. All right, so this is the gas solubility. This is Henry's law. This is your gas solubility. All right, and it is directly proportional to the pressure. So the more pressure you put on that gas, the more that gas is going to go into your solution. And then you have a constant, Henry's law constant. And so you're going to have a constant for oxygen, for nitrogen, for carbon dioxide. Any gas is going to have a Henry's law constant. So if we look at a gas, we see that if we solve for the constant, K sub H, Henry's law constant, that is simply S over P. Divide both sides by P, you got S over P. That is your Henry's law constant. All right, so if we take a solubility at a given pressure, and then we want to know what is this solubility going to be at this other pressure, all right, given that this is the same gas. All right, so if you have the same gas, we're looking at oxygen, or we're looking at CO2, we have, solubility of oxygen at some pressure. What's the solubility of oxygen at this second pressure? So then the constants for oxygen are the same. And so you can have S1 over P1 is equal to S2 over P2. And so you can have this equation for Henry's law, right, without actually using the Henry's law constant. If it says, give me the answer for the Henry's law constant, well, then you have to take one of the solubility of 1 over the pressure 1, or solubility 2 over the pressure 2. That will give you the same answer because it is a Henry's law constant for that gas. All right, so here is your piston. Here's all your gas molecules here. This is CO2. You're going to carbonate your beverage. You're going to increase the pressure. You're going to push the CO2 into your liquid. All right, you're carbonating your liquid. All right, so that's how they will carbonate your sodas, your waters. And every time you open a soda or water that's carbonated, you will hear the release of the pressure of CO2. All right, and so then it will escape over time, and then you will have your flat soda, your flat water that used to be sparkling water is no longer sparkling. All right, so again, you increase the pressure, you will increase the solubility, more gas molecules into the solution. All right. Solubility of pure helium in blood is 0.94 grams per milliliter. What is the solubility of helium at a depth of 1,500 feet? All right, well, we need to know what that pressure is. So here is the solubility, 0.94 grams per milliliter at a pressure of 1 atmosphere. All right, so the pressure increases by 1 atmosphere every 33 feet of depth. So if we go down 1,500 feet, the pressure is all the way up to 46 atmospheres. So we want to know what is the solubility now that our pressure is 46 atmospheres. When you go down 1,500 feet, your pressure is now 46 atmospheres. All right. And so you have your equation, which was S1 over P1 is equal to S2 over P2. So you got your 0.94 grams per milliliter, grams of helium per milliliter of blood. That is the solubility of helium in blood at 1 atmosphere. What is the solubility at 46 atmospheres? All right, so then again, to solve for this, you got to multiply both sides by 46 atmospheres to get rid of the 46 atmospheres here. 46 atmospheres cancel. All right, so again, your units, they have to be the same. Units, they have to be the same. All right, so we don't have a temperature in this one. It is a pressure and a solubility. The units on both sides just have to be the same. And so your answer is going to be 46 times 0.94, and that's going to be units of grams of helium per milliliter of blood for the solubility of helium in blood at that pressure. All right, and so the two sig figs, you got 43 grams of helium in 1 milliliter of blood. So the solubility of helium in blood, 43 grams of helium per milliliter of blood at a depth of 1,500 feet, which has a pressure of 46 atmospheres. So again, you increase the pressure, you increase your solubility. The pressure went from 1 atmosphere, and it was 0.94 grams per mil, up to 46 atmospheres. Now it's 43 grams per milliliter. All right, so this one's interesting too. So most fish have a very difficult time surviving at elevations above 1,500 meters. All right, and so the problem here is that fish require oxygen. And so the higher elevations have a much lower pressure. So as you walk up the mountain, it's less and less pressure, less and less oxygen. All right, and so that is the same because if you have a lake, the pressure pushing down on the lake pushes the air into the water. Once you are above 3,500 meters, all right, then the pressure is not enough to put enough air into the water. And so that means less oxygen in the water, and fish cannot survive without oxygen. All right, so the decreased solubility of air, which contains your oxygen in the water, so that's not enough for these fish to survive. So fish require a certain minimum level of dissolved oxygen to survive. And at a low pressure, high altitude, there's not enough oxygen in the water for the fish to survive. All right, a lot of this chapter is going to be calculating different concentrations. And so the 4 concentrations we focus on the most are going to be molarity. Remember, that's moles per liter. Mass percent of a solute, so that's mass of your solute divided by mass of solution times 100 because it says percent. Molality is new. Molality is moles solute liter, no, that's up here, kilogram of solvent. All right, so we should put up here moles of solute, liter of solution. And then mole fraction, that's going to just be your moles of solute. And then you could say moles of solution, but you can't get there directly. And so you will say moles of solute plus moles of solution. Right. So it is, again, it's moles of solute over moles of solution, but the solution is solute and solvent here. Or you could have just wrote moles of solution, which means moles of solute plus the moles of solvent to get a mole fraction. So fraction, you do not multiply it by 100. That would be 8%. So Again, molarity, capital M, mole solute, liter of solution. You need to know that's the units for molarity. Mass percent, you need to know that that's going to be the mass or grams of solute divided by the mass or grams of solution. The units just have to be the same. Doesn't matter if it's grams, kilograms, whatever mass units they are. Normally it is grams. All right, so if we had an experiment and we need 36 grams of 5% potassium bromide, how would we make up this solution? So we need 36 grams of a 5%. So anytime I have a percent, I always, just like when we did limiting reagent, you have 100 grams of solution, because solution is total. So if we have 5% of an aqueous solution, so I assume 100 gram sample of this solution. That means that I have 5 grams of potassium bromide and 95 grams of water in order to get 100 grams of solution. All right, so your solution is your solute plus your solvent. All right, so I would always write this out when I have a 5% solution. 5 grams of potassium bromide, 95 grams of water, 100 grams of solution. All right, and so we want to make this solution. Well, if we wanted to make 100 grams of solution, it would be simple. You just take 5 grams of KBr, 95 grams of water, and you got 100 grams of the solution. All right, but we want to make 36 grams, not 100 grams. All right, so you need 5 grams of KBr if you want to make 100 grams of this solution. The question is, how many grams of KBr do we need in order to make 36 grams of this solution? And so we simply multiply both sides by 36. And we get we need 1.80 grams of KBr, and then it has to add up to 36 grams of solution. So that means we need 34.20 grams of water. All right, so when you solve for this, you get the mass of KBr, which was 1.80 grams if I multiplied my numbers correctly and then divided correctly. All right, so I know that I need 1.80 grams of KBr to make 36 grams of this solution, which means I needed to add 34.20 grams of water, because here's my solute, here's my solvent, and here's my solution. All right, and we will pick up there next time.